Assalamu alaikum and good day everyone. So welcome to this video presentation about chapter 4, first section. In this section on this video as well, we will be talking about the moment of a force in term of scalar formulation. Also, we will talk about the cross product, how to find it, what is this, for what its formulation, as well as we'll talk about a vector of moment, force vector, a principle of a moment, etc. So we try to make this video quite short, just to discuss about the concept of this chapter, section of the chapter. So let me share my screen here. Okay. So hopefully, after having this short video presentation, we'll be able to understand and define the moment, and also to determine the moment of a force in 2D and 3D. Moment is the moment of a force about point provides a measure of the tendency of rotation. So it's not necessary it's rotating, maybe it's already fixed. There is counter moment there to resist that moment, or maybe it's already rotating. But that's why we say the tendency of or for rotation. Sometimes we call this rotation as a torque. Now the force, and there is certain arm of rotation in between them, has to be perpendicular to it, of course. We call it as moment. I give picture here is give different case scenario when we have this similar force. Let's say this is 100 here, 100 Newton here. It's all Newton, 100 Newton here. And then we can see different moment being generated in each case. In the first case, we will have 100 times the distance will give us 100 D. In the second case, we have some declination here, and there is the only one that cause moment is the vertical one, when we have vertical angle between them, while the one that goes through the point of rotation, it will have zero moment. We will talk more about this, just beginning to say ABC of this chapter. In 2D case, the magnitude of moment, let's say in this particular example, we have this plane, and then there is point of rotation, we call it point O. And then we have a force apply on this plane, okay, circular shape, let's say here. This will generate a moment about point O. So we're having certain perpendicular distance from point O to the action point of the force vector here, cause a moment. Now, of course, depend on the direction of that force, the moment will also gain certain direction. As shown in this particular example, D is the perpendicular distance from point O to the line of action of the force. And in this 2D, the direction of moment about point O is either clockwise or counterclockwise, depending on the tendency of rotation, as I mentioned. If we want to talk about the scalar formulation, then the moment here will be caused by the multiplication of force multiplied by the vertical distance of that force. If the force come in inclination or declination, depends on the direction, it has to be analyzed into F and Y, Fx and Fy component. Why? Because we want something, only the force that has a vertical effect on the point of rotation. So that's the one that can generate a moment. So for this case, the f here being analyzed into fx and fy. You can see the component here for fx is this arm. This is the vertical arm between fx and point O, right? So this is the arm, and the rotation is going clockwise. If we use the right hand rule, when you do clockwise, right, your thumb will go to the screen. You do clockwise, same as the rotation of the clock. You do clockwise. The thumb represents the moment, okay? This movement here goes to the right is the force direction, and then this is the D. This will cause moment about this axis, and M goes straight to the screen. This means it's a negative. Okay, if you do it like this, you want to have this top view, you do clockwise, you go down, this is negative moment. If you do the otherwise, which is counterclockwise, you'll do this way, this is the force, this is D, then you do counterclockwise, your thumb will go up, right? So this is a positive. So from here, we can conclude this is clockwise, which is negative moment, right? This is negative moment. Why this is important? Because this will affect the magnitude. Eventually, we will find at the end, right? Now, how about Fy? You can see the arm of Fy from this point up to point O. The vertical arm of rotation is this, which is arm A, right? So this will cause, let's see, now this is the point, this is support. Imagine this one is a solid or as a clock, like this is the clock, this is point O here. Now this is the force going like this is Fy, right? Now, of course, it's going to be counterclockwise. So this will go into this direction, and it's positive, my friend, right? Use the right hand rule to find out. Now, moment about point O, what we can be written here will be Fy multiplied by A minus, because this one is a positive one, that's why I put it in the beginning, minus Fx multiplied by B. This is the one. So this gives us the moment about point O, and this is in 2D. Any problem like this, you can solve it this way, and it's quite simple, okay? This is another example when you have different direction. So you can also analyze them. This will be in this direction, Fy, Fx will be this. You can see here, Fx has a different, effect. Now this is the arm here, same B, but it will give you what? It will give you counterclockwise. Now it became positive, while this one give you clockwise, so it became negative. That's why they wrote it in a different form here. That's why you have also to be quite precise and accurate on how to judge and conclude the rotation direction, right? So how about in case if we have 3D, does it still work when we have two vector in case of ijk or xyz? This formula for FD, it doesn't work easily because you have multiple D. So better we use the cross product here. We can see this is the rule for the right hand of the cross product. When we have two products and there's certain angle between them, you can say this C, the determine here, magnitude of it will equal A vector multiply or cross product with B, which equal AB sine theta UC. And the UC is the unit vector perpendicular to both A and B vector, which is the plane of these two vectors. And so the way how to find these is we can use this IJK coordinate system, which is the Cartesian one. And of course, when you multiply I element with I, it will equal 0 based on the definition. Just now we had the sine theta due to the sine theta. So we can have this, for example, I multiplied by j will equal k. And always when you go from I to j is a positive, from j to k it's minus. So it will be I minus j plus k. This is the case when we do the cross product later on. This when we have two vector and we try to do this cross product, because remember later we can have m equal r multiplied by f, or you can, this is could be r or d. This is what I mean is the vertical distance between the force and point of rotation. So it could be d, but once we have vector which has involved ijk, we use r. Anyway, but let's see, this is c equal a cross product with b. On this vector ijk, you open this row, then we have all component for a in terms of ijk, a line here, and then we have the all component for b vector, which is ijk as well. We can write it as bx, by, and bz. Now we take each element separately, just for illustration. For I, it's you can see it's in the first row and first column, so we cancel these. Okay, now we left with ay, bz, and az, by. So as you know, the determinant, this one can be found like we say I, this is the one of selection, point of selection, will equal ay bz minus, so ay bz minus az by, right? This is the rule. When we come to j, remember this sign, right? We have plus, minus, plus. So plus I, then the determinant, minus j with their determinant. So j here, as you can see, is in the first row and second column. So we left with the I and k component only. So we have ax bz minus az bx. Same goes to k element. This is k is in the first row, third column, and so we find the determinant from here, ax by minus ay bx. And then we just combine all of them, I minus j plus k, with respect to the value in each component here. For example, this one here, this magnitude here, and this magnitude will be here. This is when we have two vector normally. Now, how to apply this one? We will use a moment here. As I mentioned, it will equal r cross product with f, and this will equal the product of r, let's say I, j, k again, right? This will be minus here. Then what we have here is r product, rx, ry, and rz. Here we will have f, x, fy, and fz. And then we do the cross product for each element I, j, k, as we learned previously. And then we have one example already given there. You may practice on it and try to solve the other unsolved problem. And we will continue talking about this subject in details with more practical exercises during the lecture, inshallah. Thank you very much. Wish you a very good day.